Good afternoon and welcome everybody. Thanks for coming. So as Franz mentioned, I'm going to present the work that I did under my 5 years as a PhD student. So I'm going to try to do it in a very descriptive and non-technical way. So if someone has a question afterwards, I'm willing to happily go into the details. But to start with, this is a house which could be made of any material. This is how people used to be many years ago, isolated one from each other, growing their own products, go out in the morning, hunt, come back in the evening. But as society evolved, people started to gather together and create populations. And that became even more important, even more patent after the revolution, like industrial revolution. Then cities started growing and people started like living all together, big vertically, close to each other, cities started densifying. And nowadays, especially in Sweden, those high-rise buildings, just because Sweden is the third largest country in the European Union and 70% of it is forest, in Sweden, most, or not most, but many of these buildings, and growing, they are made of wood. The problem is that even though they comply with the present regulations, acoustics regulations, as Nikos talked about before, people still complain. They say, yeah, they may pass the regulations, but I'm not happy here. So one first kind of objective of my thesis was to try to understand why people complain in that. So the first aim, we could put it try to find design indicators of how humans perceive vibrations more. I focused quite much on the low frequency range. Well, the other point of my dissertation was you have to believe me on that, but there is a big difference whether in one building we use some type of floors or some other type of floors and stuff like that. Whereas this is quite easy to predict in heavy structures like concrete. Wood is a natural material. It's very unpredictable. It depends quite much if you have knots, if you have resin pockets and stuff like that. So due to that variability, it's quite hard to predict the behavior of a wooden structure. So therefore, the second aim of the thesis was to try to create and develop computer models to try to predict the behavior, the vibroacoustic behavior of these buildings during the design phase. So if that ultimately could be achieved to some extent, there would be cost and saves for the industry, and then ultimately vibroacoustic comfort could be achieved by the inhabitants. So this is everything which was driven at during the 5 years PhD. So I will just go a bit more deep into the details. And therefore, the title was Vibroacoustic Performance of Wooden Buildings, Perception and Prediction. So wooden multi-story buildings in Sweden, they were allowed during many years, but due to numerous urban fires during the 1800s, they were prohibited, and that century-old ban was lifted in 1994. So all of a sudden, those buildings started growing popularity, just increased market share, just because wood is very cheap, is very abundant in Sweden. It allows a high degree of prefabrication. That means that you can just build indoors as a factory, transport it to the building site and just put up a puzzle as a building, and that is very important in a country which bad weather like Sweden. And it has a nice environmental friendly, so it has a lot of advantages. But as I said, we have two big problems which are in our field, or the field that I'm dealing with, which is the variability, and due to that, the acoustic comfort. So we can distinguish in any building, but now focused on wooden buildings, two types of sound transmission. One which is called airborne sound, which is where most of the sound energy is transmitted through air. I speak, then it goes and my voice hits a wall and radiates to the other room. That is airborne sound. And there is another one which is impact sound transmission, which is the sound that we hear down here when someone up above us strikes directly the floor. It can be people walking, it can be objects dropping, it can be any source you want. So nowadays, the current ISO standards, and now I'm going to focus on impact sound because it's the one which has more importance or that is more critical in wooden buildings. The current ISO standards in Sweden, and Sweden is the only country in the world which has account for frequencies below 100 Hertz. the only country in the world that count from frequencies from 50 hertz to 3,000 to 5,000 hertz in impact of 3,150. So the problem with those ISO standards is that they are identical for concrete heavy buildings and lightweight buildings. So when they were developed, they just were made for buildings, concrete buildings, because the wooden buildings were prohibited. So when buildings were reintroduced, the wooden buildings, they said, but we use the same norms. The problem is that the low frequencies are out of the scope, frequencies below 50 hertz. That means that they're not accounted for, and that means that that could trigger some type of problems. As a matter of fact, this is an excitation source, which is called the tapping machine, which is like 5 hammers which alternatively hit the floor, and then you measure the sound down in the room below. So you can assess, by using this source, you can assess how a building, how good your floors are against impact. So if you compare the force that they create, these tapping machines, against daily activities, this is a plot from a Norwegian researcher called Anders Holm, you can see that the force that the tapping machine creates underestimates very much the hail impacts, which are daily activities that happen in wooden buildings, meaning that if you look at frequencies below 100 hertz, actually the daily activities are much higher than those that you could evaluate or predict or assess with this tapping machine. So based on that plot that we have here and other things, there was this Swedish research project that I was involved in called Aculite, where we measure impact sound from 50 hertz to 3,150 in wooden buildings. And then we asked people via questionnaires, how do you feel about living conditions here and stuff like that. So if we compare those standardized indicators from impact sound, which go above 50 hertz, with people's responses to questionnaires, the correlation was around 52% or something, the R-square correlation statistically. Whereas if you include frequencies down to 20 hertz, the correlation skyrocketed up to 83 or something. So that points out that in wooden buildings, when they are very light, they are very easy to put into movement, then low frequencies are of importance. Then another question is, how do you address those frequencies below 50 hertz? Because are those vibrations? Are those sound that you can measure with a microphone? That's another question. But the whole thing was to, if vibroacoustic comfort is to be achieved in these type of buildings, and again, we are focusing very much in the low frequency range, we have to dig more into human perception of vibrations, and also to try to improve the correlation with the standards, and also to try to develop prediction tools, which you can actually predict the behavior of a building before it's actually erected, and then you can just save time and money for the industry. So, as you can see, if you are to develop a prediction tool and see how people perceive sound, you have to work on 3 aspects. One is the excitation sources. If we are to create computer models that want to predict the actual impact noise, how do we model those sources in the computer? We have to model them in an accurate way. Second of all, how do we model the floors? Wood, as I said, is a very orthotropic, variable material, which has to be very much thorough thought, because it's not that straightforward, it's not homogeneous. So you have to take a look, one has to dig into how to model the actual floor construction. And third of all, once that sound travels through from the excitation source to the room below, how do people perceive that? So this is a graphical summary of what I did during the PhD dissertation, that I will be coming to that one during the whole presentation. But this is, we tried to start at the big picture. I'm gonna model a building. The first conclusion for that was, you cannot do that. This is a too complicated thing. So take a step back and look into different details before you try to put up a whole building. So in one of the papers, what we looked into was there are some kind of elastomers. Sorry about that. In the first paper, paper B, what we look into, okay, normally you have like a wooden floor is made of like a flat surface, and then you have beams and stuff like that. the calculation time of those floors, when I put like some kind of excitation in them, will depend very much on what you model. So the first thing was like, okay, in order to be accurate but not have too much time in it, how much do we need, how much level of detail do we have to consider? Do we need to model the air that there is here between the cavities, between beams and plates? So that was one thing that we looked at. The second thing was to, okay, there are a lot of modern constructions, type of buildings that use some type of rubber materials between floors and walls in order to reduce vibration transmission, flanking transmission. So it's like, this is a quite complex material, so how do we model that? The third step was to take a junction, which is where a lot of difficulties happen when beams meet on top of a plate or a plate, two plates meet on top of a beam. How do we address these type of junctions? And how do we address it in a simplified way? Of course, you can go that much into detail as you want, but the good thing is that ultimately these should be used by industry. And that should be, probably they don't have the time to sit down and calculate 3 sheets of paper of equations. So it's good to give some type of guidelines that is easy to use. The next one was to kind of how to model the excitation sources. And the last one was the transducers. How do we measure? These I will not talk about it, but most of the measurements that we did during the thesis were done by accelerometers that we developed and calibrated in-house ourselves. So as I said, I'm going to go a bit more deep into detail now in just one slide of each paper. But the first paper, as I said, the research question there was like, is it possible to create a prediction tool, finite element prediction tool, of this type of building with existing knowledge? As I advanced before, the question was no, it's not possible. So what we have here is a building which is made of boxes, stuck on top of each other. I didn't believe in the first time when they told me, yeah, but these type of timber volume elements, they are boxes stuck on top of each other. I said, yeah, sure, but they are. I mean, we went up to the factory and they are boxes which have all appliances, furniture inside. So you just come to the building site, stack them on top of each other, and just put some type of elastomers in the middle in order to reduce flanking transmission. So compared to traditional buildings here, that if you apply a force on the upper floor, it goes directly through the partition and also through the walls. In these type of buildings, you force the vibrations and the sound as well to go through the flanks, and hopefully you will reduce it with those elastomers there. What we tried to do was to compare, for example, here is just a extract of some results. We tried to compare this TV building with the normal building. We put a model, 2 boxes, here is a cutout of that model, put a force in here and measured both vibrations going up on this wall and going down. If you look at the lines red and blue when I show this, you can see here on the left that these lines blue and red lie totally in the 0 level. That means that we have total reduction of vibrations, and we know because of measurements that we have performed that is not the case. So the main conclusion of that was that this is an unrealistic behavior. We need to take a step back, as we said, and look a bit more into the details. And that's what we tried to do. The second step was to try to look at the acoustic median cavities. Is it necessary to include air and insulation in the cavities when developing these prediction tools? As I said, the fact of simplifying the models or not can actually, you can gain a lot of time, calculation time. We are talking that maybe some model like this would take 1 week to calculate or something. That's why it's important, if this eventually will be used by the industry, time is money, to come up with as many simplifications as possible while still keeping the accuracy so they can actually rely on that. So let's see if this works here. So what we said here, what we see is like a scheme of a model, a module on top of each other. We apply a force here, and then we measure it or we evaluate it in the room below. We try a lot of different models, how to model the insulation, how to model the air, a lot of different things. This is just one example of a result. And the main conclusion was that, yes, you actually have to consider air and insulation when actually creating and developing finite element models. So that was not good, because you will have to do a lot of extra time with the modeling and a lot of extra time in the calculations. The third thing that we looked at was to how actually can obtain reliable material properties of elastomers when we put them into those models, because we will be able, if we are to model real buildings, we will have to model elastomers. So normally when you buy an elastomer, we focus here on one that you can see how they can be used. I mean, this is just a support that we did in the lab with elastomer. You can just put into 2 pieces of wood. So normally when you buy one of those, what you get is a kind of a catalog, a data sheet of the product, and the properties that you get in there, they are very much dependent on the conditions the tests were performed. And what you want is not parameters, material parameters that are test dependent. You want material parameters where you can actually model different and arbitrary sizes. So what we did was to try to develop a characterization method where you have some properties that have nothing to do in the data sheet with the ones that you actually want, because you want to kind of sometimes, if you want to predict the building, just how that will be performed, you said, okay, but I'm going to try to use a strip, or I'm going to try to use blocks instead. In order to do that, you need material parameters, which you don't get from the data sheet. So what we did here was to develop something that from that test data get the material properties that we want. Moving on a bit, the next that we looked into was how can, now we know that we have to put air in the cavities. We know that we have to put elastomers between floor and walls. And the next is these beam plate connections. How do we model them? I mean, if you look at a floor like this is a lab test that we did. It's just basically beams with a secondary space boarding and plates on top of it. You don't see that, but you have to believe me, there is 2 types of junctions in that floor, which is 2 plates meeting on top of a beam and 1 plate going over a beam. So what we did was to create models in the computer with different configurations of just these junctions, without or with glue, because normally in this type of floor you have to use screw and you glue. So it's like if we can actually avoid, for example, modeling the screws, or if we can actually avoid modeling the glue, it'll be a big, as I said before, time and costs savings. So what we did was to create some cutoff of a real floor. We put a lot of accelerometers there, and then we did measurements. After those measurements were performed, we modeled that T-junction, that junction in the computer. And that was, once that junction was validated, we played around with it. We modeled the glue, we put the glue and studied differences between the model results. Since my first model was validated, then we said, okay, but the differences that we have here, the relative difference will also be if I play with the models instead. So the result of that study was to create guidelines and based on parametric studies on the screws, on the thickness of the glue layer, on the type of adhesive that one should model, if you have to consider it, if not, and stuff like that. And one other thing that I told in the beginning is the excitation source is one thing that you have to look at. What we did here was to implement the tapping machine, which is a standardized source in the models. I will not go into detail here, but what we tried to do here was to save time. Normally, if you do time domain simulations, it takes a lot of time. However, we proved that by doing it in the frequency domain and doing some different scaling here, you get to the same results. So basically, we tried very much in the same way as before, that you tried to just cut down in details to gain time. Here it was more or less the same. Try to model this source, but lowering the calculation time. And finally here, we focused on how people perceive the vibrations. So we call it a psychovibratory test. We put 5 floors on the laboratory, real floors delivered by manufacturers, and we did 2 different tests, a seated test and a walk-in test. So in the first walk-in test, we had like 60 people participating and 5 floors. In the first test, in the first one, we told people to walk back and forth between those 2 lines, measuring the accelerations they created with accelerometers in those crosses. So they walked back and forth, and then we gave them a questionnaire asking about how do you feel about the vibrations, how do you feel about the noise that you created, very much along the lines that Nico presented in his study, but applied more to vibrations. And the second sub-test, there was a seated test. The test person was seated on a chair, where we also measured the vibrations he was exposed at in those 3 spots, on the backrest, under the chair, between the feet. And then me or another colleague walked back and forth. And we sent another questionnaire. How do you feel the vibrations that we created for you when you were seated? So here you have like 2 pictures of me performing the seated test while Anders, my colleague, was walking back and forth, or me being ready to walk between the 2 lines. So during the subjective test, as we said, we measured accelerations that the people were creating or exposed to, and also we send out questionnaires to them. And also, apart from all that, we measure objective parameters of the floors, dynamic properties like eigenfrequencies, eigenmodes, damping radius, and stuff. By doing some statistical analysis, massaging all the data, we kind of came out with some design indicators to floor vibrations. Like if you follow this, people will not be annoyed, and it will be accepted from a vibration point of view, this floor. And if you go over that, it will not. So some kind of indicators. I should point out that this is not something written in stone. It was just 5 floors, but at least it showed trends to follow then. So to conclude, the aim of the PhD project that I was doing was to predict low frequency sound and understand how humans perceive vibrations. And we did research in the prediction side by looking into elastomers, the air cavities, the connections, and the excitation sources. And also efforts were put into perception, which was to come up with some type of design indicators for vibration annoyance and vibration acceptability. And finally, some measurement techniques that we developed, or sensors, transducers that I didn't talk here. This green box summarizes a bit what we did into the research fields. So, yeah, it's done. So, did what we did, but still we're working now into how to assess uncertainties a bit more, and how to optimize calculations to reduce more time, to do some model reductions and stuff like that. Once that is up and running, probably you can just predict the behavior of a building, and people will be happy. So thank you very much for your attention.